are inverted stacked CDP traces and models based on the sonic and density log. Analysis of amplitude versus offset is fundamentally different from study of conventional stack sections. Based on theory expressed in the Zoeppritz equation, the value of amplitude as a function of offset is not only dependent upon the compressional wave velocity and density, but upon the shear wave velocity. The study of seismic amplitude as a function of offset is called AVO, for amplitude versus offset. The Zoeppritz equations that describe the amplitude versus offset response can be simplified to include only response values with an angle of intercept less than 30 degrees. Following standard nomenclature, we use Vp for the compressional wave velocity, Vs for the shear wave velocity, ρ for density, and sigma for Poisson's ratio. The equations contain several terms, but can be additionally simplified into a simple linear equation with the y value being the amplitude response. The slope or gradient is a complex term with the p wave velocity, s wave velocity, and Poisson's ratio as controlling factors. The intercept is equal to the amplitude at zero offset. It is the response measured by the borehole sonic log and can be very different from the full offset stack. We use the term R0 for the zero offset amplitude and gradient for the slope. These relationships can be explained by considering the amplitude of gas-bearing and wet sandstones as a function of offset distance from the seismic source. The illustration shows the simple travel path for three offset distances that are 1, 12, and 24 groups separated from the source. For the gas sand encased in shale, its response is a negative trough that has increasing deflection at the far offset. For the wet sand, the response is a weaker trough due to the absence of the gas. For the wet sand, there is a slight decrease in amplitude from near to far offset. When the amplitude versus offset relationships are displayed in a plot, they yield insight into the Vp-Vs ratio of the rock, and hence Poisson's ratio and fluid content. There are several different plots that are generated to display the AVO relationships. A typical method of processing is to use a single layer approximation to calculate the angle of incidence. One common method, called recon AVO, is to use the stacking velocity data and a simple one-layer case to calculate the angle of incidence. Once this is done, a linear regression is fit to the amplitude values for each seismic time sample. From this linear regression, it's possible to calculate the zero offset amplitude value, R0, and the gradient, G, for every sample of all traces along the line. This principle may be thought of as an alternative to conventional stacking. The stack is the average amplitude at all times. The recon AVO is a linear regression fit to amplitude as a function of incidence angle. Once R0 and G have been calculated, they can be plotted as wiggles just like the seismic trace. Other plot types have been suggested, including the product of R0 and G and the sum of R0 and G. An alternative interesting plot convention suggested is a composite plot formed by overlaying the black wiggle version of the zero offset trace over a color that represents the product of the sine of the intercept times the gradient. If we consider three types of gas sands, the significance of the composite plot is clear. For gas sands with a strong negative zero offset reflection coefficient, the gradient is also negative. The product, therefore, is positive. The plot convention uses a red color for positive values of intercept times gradient. A gas sand with a positive zero offset reflection coefficient has a similar negative slope, but has a negative product. It, by plot convention, is assigned a blue color. The merit of the composite plot becomes evident if the model response to a simple gas sand is considered. In the model, the thickness of the sand is left constant, as are all the rock properties except gas saturation. The model shows the difference in the recon AVO response of a model gas sand and a model wet sand. The top of the gas sand is a red positive response with a negative reflection coefficient. Since the response is the product, the gradient is known to be negative. The base of gas has a positive slope and a negative reflection coefficient. Thus, the base of gas sand is also a red positive response. The convention of the R0 times sine of gradient plot overcomes the confusion that can be generated by the change in gradient at the top and base of a thick bed. In the composite plot, the Recon AVO response of the top of a wet sand is a weak trough with a blue color. The negative reflection coefficient with a blue positive response is typical of a negative gradient. The base of the sand is a dim peak with a blue color. This represents a positive reflection coefficient and a negative gradient typical of a wet sand. The method of interpretation of Recon AVO displays is exactly analogous to conventional seismic character interpretation. The AVO response is identified on a plot of the data and compared to models made from well control. The models are used to interpret the response of the lines. Now let's talk with Jack Ward, President and General Manager of Simon Geolithic. Does Recon AVO work equally well in all geologic environments, or is there a particular type of AVO plot that's especially suited for a set of rock conditions?
In order to answer questions of that type, we selected 3 different geologic areas to test the Recon AVO response. The 3 areas we selected are the Eocene of the North Sea, the Eocene offshore Sumatra, and tertiary sands from the Gulf of Mexico. A comparison of the Recon AVO response for the 3 geologic settings indicated that there is a distinct preference of certain geologic settings for Recon AVO types. The R0 plus G plot turned out to be almost universally acceptable. It was a good plot for the low velocity sandstones and a good plot for the limestones. The R0 times G plot, on the other hand, turned out to be very environment specific. It's only a useful plot in the low velocity gas sands. It's a very poor plot to use in high velocity rocks. The R0 plus sine of G plot turned out also to be a useful plot for nearly all of the environments that we considered.
I'm specifically interested in the high velocity sandstones. I thought that Recon AVO displays were most useful for low velocity sands with gas.
I think the best way to answer that question is to consider the response of the Eocene sandstones from the North Sea. One way to look at the response of the Eocene sandstones is to look at a graph of the amplitude versus offset response for the Eocene turbidite case. If we look at the ordinates of the graph, we can see that the graph is oriented with the angle of incidence on the horizontal axis and the amplitude on the vertical axis. If we look at the velocity contrast, we can see that the P-wave velocity contrast shows us that the shale has a velocity of about 2,156 meters per second, while the sand itself has a higher velocity at 2,578 meters per second. Thus, we have a velocity increase and would expect a positive reflection coefficient. However, if we look at the density contrast, we see the density decreases from 2.18 in the shale to 1.86 in the sandstone, so that we have a velocity increase with a density decrease. So we have a very weak reflection coefficient at 0 offset distance. The Poisson's ratio change is a decrease from 0.37 in the shale to 0.18 in the underlying sandstone. So if we look at the amplitude versus offset response that goes with the top of the Eocene sandstone, we find that we start with a very weak positive reflection coefficient and at increasing angles of incidence corresponding to increasing offsets. We find that the amplitude actually decreases with an angle of incidence about 10 degrees and actually becomes negative between 20 and 30 degrees incidence. If we look at the base of the sandstone, we find that we have a velocity decrease, and that's exactly opposite to the increase at the top of the sandstone. And the chart shows that amplitude is a increasing function of offset in a manner that's almost exactly reverse to the top of the sandstone.
It seems to me that the polarity of the event changes through the gathers, so that some of the event is positive polarity and some is negative. It's difficult to predict the effect of stacking, but it's obvious the stack is very different from the 0 offset response.
Well, that's just what we see in the gathers. If we look at a plot of a model gather from the Eocene turbidite of the North Sea, we see that amplitude does change distinctly as a function of offset, when we look at an event that's near the top of the sandstone. If we look at the plot, we see that the traces to the left are the near traces and the traces to the right are the far traces. If we look at the full stack response and we compare it to the near trace response, we can see on the near trace response that the top of the sandstone is actually a weak peak, while the base of the sandstone is a small trough. If we look across the peak, we see that the amplitude actually decreases and changes from a positive to a negative, just as you suggested. If we look at the result of the stack, however, we find that the polarity of the stack actually looks reversed to the polarity of the zero offset trace. That means that if somebody attempted to tie a synthetic seismogram from a borehole log, it would tie the near trace very, very well, but would actually have opposite polarity to the full offset stack.
This type of gather would show a strong AVO response. What type of recon plot works the best?
Well, we've designed a plot to show the applicability of each type of recon AVO plot to a specific geological environment. If we look at the plot, we see that in the lower right-hand corner of the plot, we've illustrated the lithology from which the AVO response is derived. We see, in this case, a high-velocity gas sand encased in low-velocity shale, and we see the P-wave increase just as we saw in the preceding graph. If we look across the top of the plot, we see that there we've listed all the different possible types of amplitude versus offset plot. At the left, we have R0, or theoretical intercept. Next to that, we have the gradient, followed by the R0 times gradient plot, then R0 times the sine of the gradient, and then R0 plus the gradient. Let's look at the response of each of those plots. The R0 plot, as we might expect, shows us that the top of the gas sand is a positive reflection coefficient and the base is a negative. We look at the gradient plot, we see that the gradient is opposite at the top from the base, just as it was predicted from the previous graph. The top of the gas sand has a negative gradient, the base has a positive gradient. If we look at the R0 times gradient plot, we see that the effect of the gradient is almost totally reduced by the R0 times gradient plot. The reason that it's reduced is that the zero offset reflection coefficient of such low magnitude, if we look at the top of the sand, we would see that the reflection coefficient would be about 0.01. If we multiply 0.01 times a gradient of negative 0.496, we find that the effect of the gradient is totally reduced by multiplying the gradient by such a low zero offset reflectivity value. If we look at the R0 sine times the gradient plot, we see that that plot has slight advantages over the gradient plot. The gradient plot can be very confusing because the response at the top of the sandstone is opposite the one at the base. Multiplying the zero offset reflectivity sine times the gradient tends to normalize that plot. So then the R0 sine times gradient plot, we actually have the same sense at the top and the base of the sandstone. The R0 plus gradient plot suggests to us that the Poisson's ratio change at the top of the sandstone would be about negative 0.216, and at the base of the sandstone about plus 0.276. If we compare that to the actual Poisson's ratio change, we see that there are slight errors at the top and the base of the sandstone, but fundamentally the values in the R0 plus gradient plot are very nearly correct. This suggests that if we look at the Eocene sandstone, that the important plots would be R0, and we need R0 if we're going to estimate the change in lithology and match it to borehole logs. And if we want to know the amplitude versus offset effect, then either the R0 times sine of the gradient or the R0 plus gradient would be appropriate plots.
Based on this analysis, calculating rock property data from a full offset stack would lead to inaccurate results.
That's correct. In fact, for a number of years, exploration and development of Eocene mounds in the North Sea has been plagued with difficulties because we get very, very poor ties between synthetic seismograms and the full offset stack. If we look at a diagram of a porous turbidite, we can probably get a good idea of what kind of response we can expect. In the center of the turbidite mound, we get a very, very dim reflection coefficient. The weak reflection coefficient occurs because the small positive acoustic impedance at the interface is almost totally overstepped by the decrease in amplitude as a function of offset. So when we stack it, we get a negative trough at the top of the stand instead of a weak peak. On the other hand, if we consider the AVO response, we would find that either the R0 plus G plot or the sine of R0 times gradient plot would give us a very strong AVO anomaly at the top of the Eocene turbidites. So when we're looking at Eocene turbidites, the anomaly plots from the recon AVO are useful in outlining the turbidites, and the R0 calculation is useful for rock property estimation.
That reasoning looks great, but I've seen excellent anomaly plots of AVO response using the R0 times the gradient displays. How do you explain that?
Well, I think the type of plots that you were probably looking at were plots that came from tertiary sands in the Gulf of Mexico. If we look at the physical response from those sandstones, we can see why the R0 times gradient plot is applicable in this geologic environment. If we look at the typical velocity contrast of a sand in the Gulf of Mexico, we'd find that a gas-saturated sand would have a lower P-wave velocity than a shale, with a velocity of about 5,260 feet per second for the gas-saturated sand, and a shale velocity at about 6,670 feet per second. The Poisson's ratio shows a very strong decrease from about 0.46 in the overlying shale to about 0.10 in the sand, giving us a Poisson's ratio contrast at the boundary of about negative 0.36. If we look at the behavior of the plot, then, we find that the top of the sand has a negative reflection coefficient, and we also, at the top of the sand, have a very strong negative gradient. If we multiply the very strong gradient by a reflection coefficient that's greater than 0.1, we actually increase the value of the response, so that the R0 times gradient display is very, very strong for the low velocity sands. Of course, the sine of R0 times gradient is an equally applicable plot, though it doesn't show the powering effect that we get by multiplying the strong value of the reflectivity times the gradient that we get in the R0 times gradient plot. The R0 plus gradient plot is probably least applicable in the Miocene sandstones. The reason that the applicability is low is that the R0 plus G plot is based on the hypothesis that the VPVS ratio is equal to 2. And here we have the strongest difference in VPVS equals 2. So in the low velocity sandstone response with gas, we have a very strong response in the R0 times gradient plot. If we fill the sand with water and we look at the water-based response, we'd find that when we put water in a sandstone, we have a very weak response when we multiply R0 times G. This occurs because the wet sand has a very, very low value of reflectivity. If we have the shale with a velocity of 70 feet per second, and we take a sand with a velocity of 6,760 feet per second, we find that the interface is nearly acoustically invisible. Thus, if we take a very small reflectivity coefficient, like 0.0019 at the top of the sand, and we multiply that very small value times the gradient, we find that the effect is the same that we had in the Eocene sandstone, and that we have almost no response in the R0 times gradient plot. So in the Gulf of Mexico scenario, the fact that we have a very strong negative reflection coefficient makes the R0 times gradient plot effective in that set of geologic conditions.
I can see where the AVO process can work for the sandstone case, but you mentioned a limestone in your case model studies. Seems to me that the rock properties of limestone suggest that AVO won't be very successful in this environment.
That's been a very common prejudice, but there's been a recent paper published by Soman Chaco in Geophysics that gives us rock property data that indicates the applicability of AVO study to porous limestone reefs. In the offshore Sumatra, in the area studied by Soman, we find that there is a direct AVO response corresponding to the porous limestone. When we look at the lithology plot that we've constructed, it's generated slightly different than the ones we looked at previously. Here we have three different types of lithology to describe: tight limestone, porous limestone, and gas-bearing porous limestone. The limestone is overlain by a shale. Here the shale has a P-wave velocity of about 97 feet per second, and it overlies porous and gas-filled limestone. At the acoustic interface between the porous and gas-filled limestone, we have a very weak reflection coefficient because the shale and the porous and gas-filled limestone have nearly comparable velocity. The tight limestone, however, has a considerably faster velocity than the overlying shale. So we have a strong positive reflection coefficient at the top of the tight limestone. Interestingly, however, the Poisson's ratio is calculated to be the same for the tight, the porous, and the gas-filled limestone, suggesting that in this area the Poisson's ratio value of the limestones is invariant for the porosity or the type of pore fill. If we look at the response of the AVO plots, then we find that the zero offset reflection coefficient at the top of the tight limestone is a peak. We have a very slight negative gradient, so that the sign of our R0 times gradient plot is actually negative for the tight limestone. The negative response occurs because the positive value of the reflection coefficient is being multiplied by a negative gradient. On the other hand, if we look at the response of the wet limestone, we find that we have a very weak trough at the top of the wet lime. Now, if we multiply the negative value at the top of the porous limestone times the negative gradient that goes with the top of porous limestone, we find that the sine of R0 times gradient plot gives us a peak at the top of the porous limestone, or that we have a positive sine of R0 times gradient plot. This means then that we're going to have a strong AVO anomaly corresponding with the top of the porous limestone. The AVO anomaly here not being generated by the differential of Poisson's ratio, but the AVO anomaly resulting from the change in density and P-wave velocity at the porous limestone.
I agree. There is an AVO response. But how is that information different from the data already available in the full offset stack response? The low velocity clearly shows the position of the porosity. So what additional information do I get by using AVO?
I think that if we look at the answer to that question, let's consider the R0 plus G plot. In this particular case, the R0 plus G response is almost exactly right because VPVS is almost exactly equal to 2. Even though the R0 plus G plot is nearly perfect, it doesn't give us a very meaningful information because the value of 0.04 is the same for all three rock types. So I agree that the response that we're seeing here is coming more from the change in the P wave velocity and the density than it is from the change in Poisson's ratio at the interface. On the other hand, if we consider the geometry of a reef, we can see that the application of the Recon AVO data allows us to more accurately depict the geometry of the reef than we can with seismic data alone. For example, if we look at the acoustic impedance at the top of the reef, we find that the reef is nearly acoustically invisible with respect to the overlying shale. The overlying shale is 24,492 acoustic impedance units, while the porous reef is 22,570 acoustic impedance units, making very low contrast at the reef. Unconventional seismic data, however, drape over the top of the reef and mounding allows us to, in general, depict the shape of the reef and correctly site wells inside the porous reef. The margins of the reef, however, depicting the exact top of the porous carbonate reservoir is a lot more difficult. And here, the AVO response changing from negative AVO at the top of porous limestone to a positive to slightly flat AVO response in the R0 times sine of gradient plot allows us to more accurately select the top of the reef of limestone than we can on conventional seismic data alone. So yes, it is correct that the response is primarily coming from the density and P-wave velocity which we have available to us in the conventional seismic, but the Recon AVO plot allows for more accurate selection of the top of the reef than we get from the seismic data alone.
So we can see that the R0 times G plot is good for low-velocity sands, but not for high-velocity rocks. It's also clear that the R0 times sine of G and R0 plus G are conservative plots in a number of situations. When considering a project for potential AVO study, should the guidelines of these case histories be used to select the proper plot style?
Well, I think the case histories are generally useful. It's probably more prudent to create a model gather from each project area before analyzing the seismic data.
That sounds good, but we all know that rock property controls the model. And by simply manipulating the variables, it's easy to get any response that we desire.
Well, that problem has been inherent in geophysical modeling for a number of years. When we make conventional synthetic seismograms, we create a model and compare that to the seismic data. Of course, the character of the model is dependent upon the input parameters. Similarly, when we make the model gather, we have to calculate the shear wave velocity, Poisson's ratio, the density, and the P-wave velocity to make the model. The way to avoid difficulty, however, is to first construct the model response based on reasonable geological variations in the area. Then select a gather from actual seismic data and compare the response from the model with the response from the data. When the model data and the real data exhibit a comparable response, then we can have comfort that the variables that we've selected for that particular geologic setting are appropriate.
You've indicated that the R0 plus the gradient is approximately equal to the change in the Poisson's ratio. What's the mathematical justification for this?
Well, that's correct. If the VPVS ratio is approximately equal to 2, then R0 plus G is approximately equal to Poisson's ratio. Now, that's something we can go to the board and demonstrate and go through the mathematical derivation, but it's probably appropriate to see if we have any additional questions before we do that.
I'm going to excuse myself before you get into that, but I'm interested in what materials would be needed to start a study like the one you described earlier.
To construct a model gather from which the recon AVO response can be calculated, it's necessary to calculate rock property data. The P-wave velocity is available in the commonly available borehole sonic log. Similarly, the density is available in a borehole density log. The shear wave velocity is a little more difficult to calculate. If a 3-component VSP is available, the shear wave velocity can be calculated from the VSP. Alternatively, a full wave sonic would be a good source of getting the shear wave velocity. In the absence of either the 3-component VSP or a full wave sonic, the shear wave velocity can be calculated by using known empirical relationships between the P wave and the S wave velocity. Once the model gather has been generated, the AVO response can be calculated for the gather. Once we know the recon AVO response for the gather, we can calculate the AVO response for real seismic data. In all probability, the real seismic data will need to be reprocessed for the field tapes because AVO processing requires special types of quality control that are likely not going to be present in previously processed seismic sections.
How much does a study like this cost?
The expense of a study like this can be minimized by first studying the well data before embarking and processing the seismic data. If a typical study starts with 2 or 3 wells and some simple geologic models, a few $1,000s would suffice to be able to calculate whether it would be reasonable to expect that there would be a significant AVO response from the geologic scenario considered. Of course, once the study has been defined and the recon AVO response is known, then seismic data reprocessing would be required and a significant study would be mandated.
Thanks.
Those were good questions. I think now would be an appropriate time for us to return to the physical significance of the R0 plus G display. This section is in response to the question on the physical significance of R0 plus G, considering the fact that R0 plus G is approximately equal to the change in Poisson's ratio. What I'm going to do now is look at the variables that control amplitude versus offset, look at the Shuey approximation to amplitude versus offset, and make a series of algebraic substitutions that show that R0, the zero offset reflection coefficient value, plus the gradient is approximately equal to the change in Poisson's ratio, as long as the VPVS ratio is assumed to be 2. We'll start by looking at the variables that control amplitude versus offset response. In the diagram, we show the incident P wave with 2 layers of lithology. The overlying layer has the typical variables for amplitude versus offset calculation: the P wave velocity, the shear wave velocity, the density, and Poisson's ratio. We let theta 1 equal the incident angle, and we'll be calculating the reflected P wave response with the symbol RG being used for the reflected wave response as a function of the angle of incidence. The variables that we have then will be, first of all, the P wave velocity. The P wave velocity here is equal to the average of the velocity at layer 1 and layer 2 divided by 2. Delta VP is simply the difference in the P wave velocity at each interface. The calculation for the shear wave velocity is exactly the same as for the P wave velocity. Vs is the average shear wave velocity at the interface, and delta Vs is the difference in the shear wave velocity at each interface. Rho, the density, is the average density at the interface. Delta rho, the difference in density at the interface. Poisson's ratio is the average Poisson's ratio at the interface, and delta sigma will be the difference in Poisson's ratio at each interface.
So these variables combined through the Shuey approximation allow us to predict the amount of amplitude, Rg, that we will get as a function of changing angle of incidence, theta. The first three equations that control the value of the reflection coefficient as a function of incident angle are based on a series of approximation by Shuey of the Zoeppritz equations. The first equation for Rg shows that Rg equals the intercept plus the gradient times sine squared theta. If we look at the values that are involved in the Rg calculation, we see that Rg equals R0 plus a term that's related to the gradient values. Within the term related to the gradient values are all the critical lithologic information that's embedded in the amplitude versus offset response. So the terms inside gradient are B, R0, the zero offset reflection value, delta sigma, the change in Poisson's ratio, and 1 minus sigma squared. The B term is a complex term that again carries a lot of rock property information inside the B term. B is a complex term that contains a lot of lithologic variables also. B incorporates variables related to the P wave velocity and the change in density at each interface. B has a second term that's also related to the P wave velocity and the density contrast at the interface. The second term of B is modified by multiplying times 1 minus 2 sigma over 1 minus sigma, where the sigma term is going to be controlled by the lithology and the fluid content at the interface. So these three equations are the Shuey approximation to the Zoeppritz equation and contain the basic variables that control amplitude versus offset. If we go to equation number 4 is the definition. And it represents the definition for Poisson's ratio. Poisson's ratio is defined by this term, 0.5 minus Vs over Vp squared divided by 1 minus Vs over Vp squared. And if we rearrange this term algebraically, we could generate a term which says that 2 times Vs squared over Vp squared equals 1 minus 2 sigma over 1 minus sigma. And this algebraic manipulation will be useful for us later when we're doing substitutions. The R0 plus G model also has inherent with it an assumption listed as equation number 5. The assumption is that the VP-Vs ratio will be approximately equal to 2. If we use the assumption that the VP-Vs ratio is approximately equal to 2, then we can calculate that 1 minus Poisson's ratio squared will be equal to 4/9. The solution for R0 plus G also involves one approximation, approximation number 6. And the approximation is that the zero offset reflection coefficient will be approximately equal to 1/2 delta Vp over Vp and delta plus delta rho over rho, or if we simply multiply this times 2, that 2 times R0 will be equal to delta Vp over Vp plus delta rho over rho. The last equation that we'll be using comes from the original Shuey definition, and it says that the gradient will be equal to B times R0 plus delta sigma over 1 minus sigma squared. The idea that we'll be using in solving this equation is we'll be using a solution for equation number 7. We'll attempt to calculate the values of B by substituting the approximations and the definitions to solve for B to show the relationship between gradient, intercept, and reflection coefficient as a function of offset. The first step in the solution of the R0 plus G proof is calculation of BR0 by substituting for R0. So the first step will be calculation of BR0, and we're going to do that by substituting into the Shuey approximation the value 2R0 for delta Vp over Vp plus delta rho over rho. We'll also make a second substitution for 1 minus 2 sigma over 1 minus sigma and substitute in for them the shear wave velocity squared over the P wave velocity squared. These substitutions will allow us to do cancellation or to use the relationship between Vs and Vp to insert a number for the variable that's present at this point. So the first substitution then into the Shuey approximation yields this relationship. And you can see that here we have delta Vp over Vp over 2R0. And the 2R0 is coming for the substitution of R0 for delta Vp over Vp plus delta rho over rho. We make a similar substitution here. This gives us an equation with R0 in both terms, and we can simply multiply through the equation by R0. This gives us BR0, where BR0 is equal to delta Vp over Vp over 2 minus 2 times R0 plus delta Vp over Vp divided by 2. We make the additional substitution here for the 1 minus 2 sigma over 1 minus sigma. This gives us 2Vs squared over Vp squared. We can simplify this equation by multiplying through by 2, giving us 2R0 plus delta Vp over Vp. This is going to leave us with a 2R0 term inside the equation. And the next substitution that we do will be to resubstitute the delta Vp over Vp in rho values for 2R0 in step 2 of the solution. In step 2 of the solution, we're going to be doing a substitution and simplifying the equation that we had in step 1. And we're going to be substituting delta Vp over Vp plus delta rho over rho for 2R0. When we do that substitution, inside the central term here, we have substituted delta Vp over Vp plus delta rho over rho for the 2R0 that was here previously. Once that is done, we can combine like terms, getting delta Vp over Vp plus delta Vp over Vp equal to 2 delta Vp over Vp. Once this has been accomplished, we can expand this equation, and an expansion of this equation would look like the equation that's here on the bottom, where delta Vp over Vp minus 1/2 minus 4 times Vs squared over Vp squared minus delta rho over rho times 2Vs squared over Vp squared is equal to B times R0. Once we've done the simplification and expansion, we have BR0 in terms of Vs squared and Vp squared. So this set of terms, this term here and this term here, will disappear when we make the assumption that the Vp-Vs ratio is 2. So that leaves us only with the delta Vp over Vp and the delta rho over rho term to remove in the next substitution. And we'll do that by, again, using the delta Vp over Vp and delta rho over rho approximately equal to R0 to make the substitution in step 3. In step 3 of the equation, we're going to remove the Vp-Vs values and the delta Vp over Vp values from the previous equation. We do that by using the assumption that Vp over Vs is equal to 2 and substituting them into the Vp-Vs values in the previous equation. Once we make the Vp over Vs equals 2 substitution, we'll be left with a delta Vp over Vp term in our equation, and we'll remove that by substituting R0 for 1/2 delta Vp over Vp minus delta rho over rho. The result of the Vp over Vs substitution is shown here. The Vp-Vs values collapse to minus 1/2 when the assumption that Vp over Vs is equal to 2 is used, and in this equation they collapse to a positive 1/2. So that if we collect the 1/2 term, we come up with the simplification that B times R0 equals minus 1/2 times delta Vp over Vp minus delta rho over rho. Now this term is equal to R0, so our final substitution gives us BR0 equals minus R0. Now at the start of this series of substitutions, we were attempting to calculate a response for BR0. And we've shown that if we assume that R0 is approximately equal to 1/2 delta Vp over Vp minus delta rho over rho, and if Vp over Vs is equal to 2, that BR0 equals minus R0. In step 4 of the solution, we return to the original Shuey approximation and definition of the gradient within the Shuey approximation. The gradient is equal to b times r0 plus delta sigma over 1 minus sigma squared. The previous set of substitutions and approximations have shown us that to a first approximation, br0 is equal to minus r0. This allows us to substitute minus r0 for br0. If we do this substitution, we find that the gradient equals minus r0 plus delta sigma over 1 minus sigma squared. Now, the 1 minus sigma squared term can be removed by assuming that the VP-VS ratio is equal to 2. If we make that assumption, we find that 1 minus sigma squared is going to be equal to 4/9. So we can substitute 4/9 for the 1 minus sigma squared. If we do that substitution, we reduce the Shuey gradient equation, saying that the gradient equals minus r0 plus delta sigma over 4/9. We simply rearrange this equation. We get the gradient plus r0 times 4/9 is equal to delta sigma. This logic and series of substitutions for r0 and VP over VS is the set of substitutions that comes up with a logic for the recon AVO plot, where the recon AVO plot is based on the logic that the gradient plus r0 times 4/9 is equal to delta sigma. This series of substitutions for r0 and assuming that VP over VS equals 2 is the logic that is behind the recon AVO plot based on intercept plus gradient is approximately equal to the change in Poisson's ratio.